Welcome back, student. I hope you have enjoying these lectures. And so far, we saw in the previous lecture about lecture 4B, and then how the explainable AI is a need, and earlier how the AI was white box, and over the time we started getting more and more accuracy. The architecture started becoming complex, and we can see that the need of explainability came up. And before the deep learning came up, how statisticians were explaining the data. Now we have heard about neural network a lot in my lecture. Then we saw basics of neural network, how the architecture of neural network and how it look like. But in this lecture we will see about how neural network learns. And as you can see that this is a better lighting condition. Earlier I was using my home to record with a basic camera and lighting, and I'm not so proficient in the creating a good lighting condition. I did try to manage, but then it was not going away. Even I currently don't know how to do proper video editing, and you can see from my lecture. I need to learn video editing as well properly. So I'm trying this lectures to this studio, and this studio is in Singapore. And let's hope we get a better learning experience with a better quality images and video. So let's move on. What we are going to learn in this, that uh, what are the forward pass and loss function, gradient descent. So in this, what we will learn basics of neural network, that what is a forward pass does, and what is the loss function, how the loss functions are measured, and how the what gradients means in the institute term, back propagation, how it happens, and how this learning create interpretability challenges in the deep learning. Okay, so the neural network learn through the repeated loop. As we see that uh, neural network learns by repeated data coming up, and it calculate the error and then it correct the error. So as you can see in this, there is this cat image, and the neural network, it has been passed to this cat image, you can see. And in this you can see that uh, it says the cat, but now prediction is saying cat, but this is actually not a cat image. So uh, it it uh, it calculate, but actually the label was been given a dog, but it predicted it as a cat, so the error came up. Now this loss is very high. So because the data given the wrong outcome, so the loss is going to go back. And that's how the neural network will learn that from the given data, what was the actual label is there, or what is actually it was. So if it predicts wrong, like if cat dog image has been given and it predicts cat, and it will calculate that, oh, I predicted cat, it was a dog image, so error is there. So it is going to calculate that as an error, and then it will try to correct that error as a from its mistakes. So just like a children learns, you keep telling them this is an apple, this is an apple, and sometime they correct it, and after a few hours they again forget what is an apple. Or when we teach them language A, B, C, D, and they learn A, B, C, D, and after some time they forget, we need to repeat again and correct it. No, what you are saying, it is A, not B sometimes. So neural network is exactly like a small children. It learns from its mistake. You have to tell them that you did a wrong, and it is going to correct its error. Now in the second image you see the dog is there, and then it passed through the neural network, and then it predicted dog, so it knows that I have done the correct prediction, so the loss calculated is going to be 0 or very low. So this way it will say, okay, I have. Then when the loss is very low, then it don't going to not going to do more correction. So primary thing to learn is a loss function. So neural network will learn that it has done mistake by calculating loss function. If loss value is high, then it is going to correct it. So it The loss function is basically a mathematical equation which is going to measure the gap between the what prediction it has made and what was actual level. Now, since the you pass the data and it does the prediction and it calculate the loss, and then so loss is going to be converted into gradient. Network is going to compute the gradient, and then based on the gradient it is going to change the weight of the connection. In the previous lecture you saw that neurons are connected with the connection, and those connections are having weights. So those weights from one person to other person connection is been updated. So basically you can understand that multiple things are connected with strings, and if that strings thickness is going to determine how strong the connection, or thin, if it becomes thin then it determines how weaker is the connection. So when weights are updated, weights can be negative and positive. So if positive weights are updated, then connections are becoming stronger. If negative weights are updated, then connections are becoming weaker. So, and then the weight update is going to happen, and then this process is going to repeat again and again. So that means with one data, the neural network is not going to learn. You have to pass multiple data, thousands of examples you have to pass to make the network learn for a particular class object. So this is going to repeat many times, and in the neural network domain, in the training domain, it is called iteration, and multiple iteration is combined together to make an epoch. So you can see the loss was calculated, cross entropy loss was calculated. We will know what is a cross entropy loss in the future lectures. It was 1.25, which is high, then it is going to be updating the gradient in a very high amount, because weights are bigger adjustment in the weight is going to happen. Now comes to the forward pass. So what is a forward pass? You see that input is there and it passed through the hidden layer. So in the neural network, we have multiple layers and one input layer, and after that hidden layer starts, and the final layer is the output layer. So in the output layer, uh, after passing through this hidden layer, and where you can see the connections are there, so this you can see the connections becoming lighter and weaker, thinner, and not getting connected. This is what actually happening. You can see the weights are not enough. So and then the predictions are made. So basically in forward pass, what is happening? You can see the radiograph image is there, and that radiograph image is been passed to the next layer. So in the first few layers, what going to happen? In the first layer, practically it is calculating the edge, the thin line kind of structures. Edge detectors are there, and that data, when it goes to the next layer, then from edge some kind of shape start getting generated, shape detectors are there, and after that combining some amount of shape, some object parts are going to be there, and then finally the prediction is going to be there. And so in the next example also you see the medical image, the it can detect the abnormal region. So this particular going to pass through this many hidden layers, and the data in those hidden layers are aggregated, and after that the final prediction is made. And let's say this is calculating risk of from the MRI image, what is the risk of, and it detects the region, and from there it is calculating the risk of abnormality. And that is how it is going forward direction, means tuck 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 tuck, from input to layer and output. Okay, then comes the prediction. So once it reaches the final layer, it is going to aggregate the what outcome is there, and then it is going to do the prediction. So for example, if a class label was dog, means input given which has the actual ground truth as a dog, but the prediction can be cat, it can be dog, rabbit, bird. So here comes the nuances. Okay, so one neural network is not may not be only detecting cat or dog. It can detect cat, dog, rat, snake, python, tiger, gorilla, bear, bird, anything. The If you are training the network for different types of data, it will be able to detect those objects or those things. So a network can be trained for detecting 10,000 different types of object, or it can be trained to detect 100,000 different types of object, or it can be trained to detect a million types of different types of object. Like you have seen that the human face detections, so it is able to detect millions of faces just from same input data coming up. So like in the airports nowadays, the face-based immigration systems are there in many countries, like in Singapore, like I saw in Indonesia. I know that in Indonesia, then in Europe, in many Dubai, in many countries, this Qatar, it has came up the face-based immigration system. So where it is able to identify from one person to other person. So is done. Similarly, the different types of objects it can determine. Now the question comes, you see the in the probability it predicts that it has been trained with four class like cat, dog, rabbit, and bird. So four classes there. So if you see 0.82 is a cat prediction in the soft after the softmax application. We will know softmax in when we learn CNN in the detail. So then the dog is 0.11, then the rabbit is 0.04, and then a bird is 0.03. Now, if you sum it up 0.04, 0.03, 0.11, and so for 15 and 3, uh, 18, and then 82. So total will be 1. So in the final prediction, any input you give, it is going to give the prediction across every class it has been trained for. So if you have trained for 10 classes, then final outcome, it will have prediction for every class that this input belongs to this kind of class with this much probability or this much score. And if you sum all the score of those 10 classes, it will become 1. So how the we say that it belongs to a particular class? So there are threshold been set in the final layer that if the value is more than let's say 0.8, then it belongs to this class, or the one which is giving the maximum probability, it will belong to that class. Now you understood. So this is how the it can give. It is not only can predict about the class, it can also calculate the numerical value of it also. Like if a house price is how much, it can also do the house prediction, or it can also uh, risk a score of a radiograph map. It can also generate the text as you see in the chat GPT, or it can also do the segmentation of the this MRI scan. So there are different tasks are there, so different types of predictor will be there, and the goal is same, that make the most useful and accurate output. So a neural network can be designed or can be trained to do different kind of tasks. So small changes and nuances you need to do. Now comes the loss function. You know, we saw the forward pass, we saw the prediction. Now is a loss function. So in the loss function, there are different kind of loss are there. So if you are making a classification kind of application, then you will have a classification loss. If you are making a prediction kind of application, so you will have a regression loss. If you are doing the segmentation of the scene, then you are doing calculating the segmentation loss. And then if you are doing the reconstruction, so you've given the input, you are trying to reconstruct the similar output, then there will be a reconstruction loss. Now for different kind of task, different types of loss functions are there. So let me be clear with you. So this like classification, regression, or segmentation or reconstruction, you can have different types of loss function for different types of tasks, and for each task you are training the model separately for a unimodal AI model. I'm not taking currently the multimodal AI model or multitask model. So let's make it simple. Uni uni model, AI models with different tasks. So as you see, for classification loss, we use the cross entropy loss function. Example loss is that, and that loss is calculated as L is equal to minus log of uh, probability of a true class. So that if it is higher when the true class has low predicted probability. Uh, Now the next is the regression loss. So now regression loss is calculated as a mean of the squared error. So the error is calculated and that has been squared, and then the mean of that loss is calculated. So it is L of 1 by n. So the number of output is there, means number of component you are calculating, and then predicted minus 2 level, and then the square is done. So it is higher when this regression loss is going to higher when the predicted value is quite away from actual value. So higher the this regression loss, that means the prediction is more far away from actual data. Similarly, for cross entropy loss, if the value is higher, then the class prediction is far off than the actual prediction. Then comes the segmentation loss. Segmentation loss is calculated in terms of, you can see the dice loss function, and it is L, which is a loss, is equal to 1 minus 2 by probability of P, the predicted mass, and the G is a ground truth mass, actual mass, how what was, and divided by predicted mass plus ground truth mass, which is in a mod of it. So you can see it is higher when, if the value is higher, means predicted mass differ quite big extents from the actual mass. For example, you can see the prediction was like this, and while the ground truth was here. So you can see this area, predicted mass has output something which was not here. So here the segmentation loss will come, and that is called necrosis. It is not able to predict the necrosis properly. Then comes the reconstruction loss. So in this particular task, it is can be calculated using mean squared error. So which is again the similar formula, L is equal to 1 by n, summation of 1 to I is equal to 1 to n. So that many number of output by x1 minus xi square. So here, you know, this each x value is each pixel point in this scene. So if it is 100 by 100 image, 100 pixel by 100, then 100 by 100 data points are going to be calculated, matching with each pixel and here and each pixel there. And this loss will be calculated and it will be squared. So if it is higher the value for reconstruction, that means the predicted reconstructed data is far off from the actual data. So what practically the model is going to do when it is getting trained, it calculates the loss, and with every iteration it is going to try to minimize this loss. Got it? So the task is minimizing the loss. Now, why this loss matter a lot for interpretability? Now the question is what? The objective of interpretability for a particular thing is that the model is getting optimized for, let's say, classification. So the we are optimizing for classification. We are making model to do the classification better. Now this classification, it is optimized to do a better classification, but the interpretability aspect need to be there, uh, because we are doing very important type of task, like let's say medical image classification. So here we are giving the loss as a goal, minimize the loss. We are asking the neural network to learn so that your loss is less as and when you are going for each and every iteration. So this loss is going to determine how the model is going to learn. Then the that is the objective. The what is model we are optimizing for. So like for classification, we are optimizing for classification. For reconstruction, we are optimizing for reconstruction. For regression, we are optimizing for regression. For segmentation, we are optimizing for segmentation. And there can be many other tasks are there. Now, error. Second point is error. What, which mistakes it has to matters, which mistake matters the most. For example, you can see that for a medical data, let's say someone, you are having a medical system developed for detecting the model classification. Okay, so model classification you want to detect. That means to tell about the patient has done, uh, means you have given the data to detect cancer or not cancer. Now, if model say someone is having cancer and that person don't have a cancer, it is not be such a big problem because someone did not had a cancer, model said it is a cancer, so doctor is going to do further investigation and test to further rule out whether the person has a cancer or not. So there are more tests is possible to remove it. Now, imagine a case where a person has a cancer and model said that the person do not have a cancer. That means false negative, which means that once the model say do not have a cancer, it will not go for further evaluation. And that person, if it was in stage 2 cancer, will progress to stage 3, stage 4, and it will be life threatening for the person. So need to know that which error matters the most. So false negative for medical kind of class, medical diagnostic kind of system is very important. False positive is not so dangerous. It can consume more test and more cost, but not life threatening in per se. So here, in this particular kind of application, we can penalize the model more if it does false negative. So that means it is telling it that don't do false negative. Whether you are doing false positive, it doesn't matter that much, but false negative, you have to minimize. Then the trade-off. Now you can, as I was mentioning in the previous lecture, that there are trade-offs are there between what we are learning and what we are accuracy and interpretability. So when we want to make very like if someone is doing too much false positive prediction, any model is doing too many false positive prediction, so in that case the model, the more and more test will be needed, and that means recall is going to be poor for that kind of system. uh, but if model is very good in reducing the number of false positive, then it is very good in detecting more sick spacing. So now in this case, we can have the trade-off between the loss function, what we want to do and not do. Now comes the gradient intuition. So if you see in the graph, uh, the we are visualizing how the loss function changes and the gradient changes. You know, the gradient is higher when it starts at this particular place, and the aim is to minimize the loss and where the gradient is going to be lowest, and then after that it can go up. So gradient helps in helping the model learn towards the minimum loss, okay, towards the lowering the loss function. So gradient is start reducing, then it model will know that I am going towards the lower loss function. And if which direction the gradient is moving also determines how sensitive is the function and how strong the signal is going to be updated. And that's the thing, how the gradient help in learning it, that is the backpropagation. So what error has been calculated in terms of loss, that need to be given back to the model, that okay, correct your internal parameters, that is a weight inside, so that in the next time you can do a lower error, because your current, this time you this prediction you had this much loss, I am giving you that this much was a error, so try to correct your gradient in your neural network, so that when next data comes you give a lower error. So in the forward pass, data is simply going forward and the prediction is done. So when the model is trained, that time the model, when the model is trained and it is deployed into the real world, that time it is only doing the forward pass. But when the model is getting trained, it does go the forward pass, it does the prediction, loss is getting calculated, and that loss will be fed back for model to learn. So you can see the loss is calculated, and then the gradient are calculated delta L by delta theta, and then this is going to pass to the hidden layer, then that will be passed to the hidden layer, and then finally every layer in the back is going to learn accordingly. So forward pass is to make prediction, backward pass to send the error back, and the gradient will tell each layer how much to update. So in the first hidden layer, which is just after the output, will have higher weights to update, and the next layer will have lower weights, and the next layer will have lower weights. So backpropagation is basically a method which is used to compute the gradient efficiently and also to send the error information back properly and the network to update its parameter uh, to the more appropriate way. Now, to update the parameter in appropriate way. So now comes the parameter update. So when the loss calculated, then the error is calculated, and from error the gradients are calculated, and then gradients will be sent back to the different hidden layers in a backward pass manner, and the parameter of those network layer, the weights are going to be updated. Now let's say old weight the was like that. So after the weight update, the new weight it can be here as per the loss map. So after the gradient update, the new weight it is going to be there. So next time it may come to the lowest loss function. So and how it has been done. So there are controlling mechanism is there, something called learning rate. So new weights are calculated is equal to old weight minus learning rate. Learning rate is eta slash n, and then the gradient. So if the gradient is pointing downhill, that means model has taken the steps to reduce the loss. The gradient can go up also if the weight calculation or the loss function or the model network is not fully trained. That time the loss can go up, can go down. So the loss function typically in a jittery manner it learns. Okay. Now, as so far we know that model is going to take many iteration and many input, and it is going to learn from many of its function. So that means it learns with a training by many examples. So you have to give many example with one data input and with one update. The model is going to not learn effectively. You have to give more data so that model will learn more effectively. So neural network learn through repeated exposure to the data. More the data you pass, and over many epochs or many iteration, model will going to gradually adjust its parameter internals, and then it is going to be effective in predicting the correct data. So you can see the many examples are there. So that many examples will be in the data set. So in the AI world, in a training world, we say data set. Data set will have many examples for AI model to train, and then those in how it is passed to speed up the training process, the batches are created. In future lecture I am going to tell you about how the batches are created. So understand that some few of the images are combined, taken together, and they are being passed at one go in the manner. So the batch of data is taken, and each batches are passed, and this batches is also the training control parameter of the model. And then these batches are passed one by one, and then each of combining number of iteration epochs are there. Those are also the internal training control parameter epoch. And after multiple epochs, we go through all the batches, and one full time passing the batch, it's called one epoch. And then initially the parameters are something, and after the training the parameter will be updated, and it is going to slowly reduce the loss function. So if keep initially the loss is high, and after that the loss function will start reducing, and after many update it will become a bit stable, and that time you will learn that we have the model has learned. So deep learning works predominantly good because we are passing a lot of data, and it learns from many examples. It repeats. It learns by repetition, just like children learns by repetition in the kindergarten or primary schools. So as keep on getting more and more data, it start learning better and better. Now, in the previous picture, you saw the training curve. So this is one example of training curve where the loss versus epoch or training time is being plotted. And as we can see that both loss, two training curves are there, green and blue. And you see the two training curve, both are going down, but one of the training curve after some time, it is going up. So best point of this training, the training to stop is somewhere just before it is start going up. So here we should have stopped. And that leads to the point that early stopping that can be applied. So in future lecture, we will know more about early stopping, what is early stopping and early stopping criteria. So at first, a model learns a useful pattern that generalizing, but after certain points, it will start overfitting. It start learning the noises if you pass more and more data. So optimal data need to be passed for model to learn optimally. Like giving more and more data doesn't mean that model is going to learn. So we will learn in the future lectures nuances of more data. And in the past also we saw underfitting and overfitting questions. So if the model after going down start going up, so basically the generalization is going away and overfitting is happening here. So you saw what we need in the model is a good generalization with a lower loss function. Once you pass more data, it start overfitting. And so good tip is that to do the early stopping criteria, the early stopping, how it does, uh, that the two curves are there, and when one curve is straight away going down, other one is started going up. So this how it done, the training loss, training time, and then so in the training time you pass certain data to train the model, and then there are process in the training called validation, so where a new data has been passed which are not being passed in the training data. So those are the new type of data, and then the validation, then the different curves are there, and then the validation loss, uh, that is called a validation loss. And if we see that the curve is going away at certain point, so this is the best early stopping criteria in the we estimate that this is a better stopping criteria. So this is to be done to avoid overfitting and also not to consume too much compute energy. So training curves are important, and they are good for visual explanation of learning. If training loss decreases, but the validation loss is increasing, uh, as you see, it says that the model is overfitted. So this is some nuances to know about the AI model training. Now, uh, there are many things are there which affect the model decision. Model AI model is not one thing, or deep learning model is not one thing. Uh, there are thousands of millions of weights are there in neural network. So that weights differences or weight can affect the output. Then there are many hidden layers are there. There are networks which have 100 layers, 1,000 layers are there. Many hidden layers are there. They can affect the outcome. Then there are many nonlinear interactions are there. So we will know in more detail. There are different kind of nonlinear functions are being used in deep learning model. Then the representations are distributed. There are training data patterns can be different. Then optimization history also lead to the sensitivity of the model training, like what was the learning rate was been set, how the early stopping criteria was set, and whether the data has been selected randomly, whether the neural network weights. So when we start training, we randomly initialize the neural network weight. We don't start from a zero weight. We randomly take the weight. So how randomly the weight has been initially set. So those all things are affect the thing. And because so many control parameters and so many way things can get affected, and that leads to the difficulty in how to explain the model. So it is hard to explain as well. You see the so many factors are interacting with each other and they are distributed in nature uh, for the entire network. So the primary key takeaway is that no single weights or neuron decide the output. So if you have an AI model with thousands of neurons or millions of neurons, one single neuron does not affect the output, or one single weight does not affect the out. It's collective outcome of the whole AI model. And there are many tiny contribution. There are many tiny neurons are there and many tiny factors are there. They together adds up in a complex way to give the output. And that's why explaining the AI model is hard. And and that leads to the thing is that the deep learning explanation is difficult. Final prediction usually caused by one simple rule, not usually caused by one simple rule. It emerges from many parameter inside. So emergence of outcome happen. And we can see that it's hard to explain. There are many input gradients are there, models are complex, there are feature attributions are there are neuron activations, different layer if we see the activation we can see. And there are many filters are there inside neural network and many hidden representation and training parameters are there, the training dynamics, training laws, validation law. There are many failure cases, how they are working. And in essence, we put together, we have to understand everything together. So basically, no single tool can explain the model. You have to attack the explainability of neural network from multiple ways, and that's going to help you understand the model internal things. So, and that is also the reason there are many explainable AI methods are there, and they are connected to the same learning process. Some method inspecting the gradients, some methods inspecting the activation function, some just to visualize the filters, neuron activation and filters, right? Learn filters, how the filters inside the neural networks are learning, and some just to visualize the learn feature, and some to study the hidden representation of the model. With this, you know right now that how the neural network learns in a very simpler way. There are forward loss function, there are forward pass, there are loss calculation, the backward pass, the gradient calculation, and gradients are passed and loss are minimized. We also learn about the overfitting, the trade-offs. We also learn about early stopping criteria, and we can see that so many things the neural network outcome affect. So we that's why so many different kind of methods are there. But when the neural networks are learning, they are simply trying to reduce the error. They are being designed to reduce the error, and but it reduces the error. But then the learning representation become distributed across multiple parameters, and multiple parameters together contribute the final outcome. So in the next lecture, we will see what are the different types. So neural networks are there like CNN, RNN, autoencoder, transformer. And if you like my lectures, to comment, share, subscribe, and put the bell activation icon on so that you can see my previous lecture. And with this, I will say see you in the next lecture. Thank you.